Well, thank you, Wendy. And I was supposed to provide a fun fact, which I haven't done. It's my fun fact that I'm usually sitting at the back trying to answer to the quiz and actually failing really badly at most of the quiz questions. So, hopefully I can do better today, given it might be something I know a bit more about than regular astronomy. Yeah. Okay. So as Wendy said, I work on mostly computer simulations, and actually you probably gave us like you've already talked about the first 5 minutes of my presentation. Anyway, so typically how do we do science as scientists? Usually the way actually we picture this, or the way we are told this is how science works, that someone makes a theory. We all have this picture of like Einstein making up a theory on a blackboard or something. And then someone else, or the same person, is going to build an experiment, and then they will come back and tell them, oh, you were wrong, which is usually what happens. Or they can say, oh, that might be right. So for instance, an example would be you had the Peter Higgs in the 60s saying, oh, there'll be the Higgs boson that is going to explain how the mass of the fundamental particles works. And then what happened, the scientists built the large collider in Geneva in Switzerland and made an experiment, and they proved his theory to work. And so you have this sort of duality here, where you have theory on one side talking to experiments, and then experiments said this is wrong, and then theorists come back and tweaks their model, and then they come with a better theory, hopefully, and until we have something that matches the data. Now, in astronomy, it's very, very difficult to make experiments because, as Wendy already said, we can't just go out and like move things around and see how they work. I can't make a star in the lab. I can't make a galaxy in the lab. There are a few small things sometimes in like astrochemistry where you can build a few things in a laboratory. For most things, they are way too big and they take way too much time, so we actually can't do any experiments. The only thing we can do is make some observations. So we have some experiments that we can do, which would be build a nice Leiden observatory, and then we can look at galaxies. But we only have like pictures in time. We almost never see anything move on the sky, and so we can't do this usual scientific method thing of going in the lab, making experiments, and then coming back and tweaking the theory. Right? We need something where we can get our hands dirty and modify and see what happens when we add more stars, or remove stars, or add more planets, or add more gas, or add more gravity, or whatever you want. And none of this is something we can do normally. So that's sort of the unique situation astronomy is in, because we can't do this normal experiment that we really would like to do. So what we do instead, oops, sorry, wrong button, is that we have our computer scientist here, and what does she do? Well, she takes a bit of theory, she puts it in the computer, and then out comes sort of a virtual universe, or a virtual set of stars. You could have a virtual solar system, a virtual moon, a virtual set of galaxies here, or anything like that. And then the game is to say, okay, now I can make a prediction, and I can compare these to my real observation. Or I can then go and tweak and say, if this doesn't work, then maybe my theory is wrong, or maybe my computer is wrong. But at least I can now go and test something, and I can test my blackboard calculation and test it. So then the game is really where this computer comes in, and where this like sort of computational physics side of things is like comes in the middle of the mix, sort of to the rescue here. So now the tricky bit is, this is essentially an art on its own, is how do we teach the computer physics, or it could be chemistry or any engineering aspects as well. It's like, how do we tell the computer how to solve the equations from the theorists, and how do we make a prediction? So if you're going to run Leiden, you've probably seen, for instance, Einstein's gravity equation painted on the wall. It's painted on the wall, it better be true because it's not easy to change. But how do I now tell my computer that I want to evolve my universe, or make my galaxies move in this way, right? And so this is actually not as easy as it sounds. It doesn't sound easy at all, but it's also not something that is easily appreciated, how the complexities of this goes. The language of mathematics is not really necessarily the same as the language a computer will understand, of how we can actually solve the equations. We can't just type in an equation and the computer will solve it. We need to have sort of an intermediate step of teaching the computer, this is how things have to move, this is how things have to change speed, this is how things have to change mass, or whatever is happening. Okay. So, and truly to the extreme of it is that if you take the simplest problem you can probably do is to take something like the sun and the earth. And this, you can go and ask, since Newton, you can ask Isaac Newton, how do I solve this? And you can take the equations and solve it exactly. You can predict where the earth is going to be in tomorrow, where the earth is going to be in a million years, where the earth is going to be whatever, in the past, and so on. And that's essentially one of the only problems that in physics we can solve. Right? The very, very few problems in physics where I can go on a blackboard and derive entirely and find all of the solutions and know exactly everything that will happen. If I just add a third thing, so you can think of just being like the sun, the earth, and the moon, or in this case I can take something like just 3 stars. If you can.
I think you go back and then if you can.
That's correct. So it looks completely random and everything is moving in all kinds of directions. And that's one of the famous 3-body problems. So I just have 3 stars, right? And that's something that people like the famous scientists have spent centuries trying to find a solution to. And say, can I just take 3 stars and predict how they're going to move? And now about 100 years ago we convinced ourselves, well, we, not me, but like scientists convinced themselves that this is a problem that cannot have a solution. Now we're talking about not solving just 3 stars, but we want to do the Milky Way, which has 100 billion stars, or we want to do the whole universe, which has millions and millions of galaxies, each of them comprising many billions of stars. So we don't have a way of taking to a blackboard and solving all of the equations by hand. We actually need, even for the simplest problems, a computer. So I'm going to just skip over. So what do we do? So to teach a computer, the easiest thing is just to say, okay, I'm going to take, instead of solving the equations, which is really impossible, we're just going to take tiny bits of universe, or tiny bits of matter, or tiny bits of stars, and then we compute all of the forces between them. And then the idea is that instead of solving the equations in one go, we're going to just do tiny jumps in time. So I know what things look like now. So if I know how things look like now, I'm pretty sure I know how things will look like in 1 second from now, because that's really, it can't change by that much. So we're going to take really, really, really small steps and move forward in time, calculating the forces every step, and taking this very slow approach to moving things forward in time until we reach, I don't know, the present day, or if we want to predict what the solar system is going to be like, how it's going to be in a million years, or if you want to do the weather forecast, it's the same thing. You take the weather now, and then you have to say, okay, what's going to be the weather in 5 minutes, in 10 minutes, in 15 minutes, and then by the end of the calculation, you know what the weather is going to be like tomorrow. And so this is the same principle. So just take these tiny, tiny jumps in time, which is very different from solving the equations by hand. So let me jump to something more interesting. So here, for instance, is an example. I think this is one of the oldest simulation for which we actually have a movie. So this is actually was made by a scientist visiting Leiden in 1962. And I know that at the time they had to find a projector to showcase the movie, because it wasn't normal that we'd go to give a talk and give a presentation that nobody had a movie. And so they had to find a projector somewhere at the cinema in Leiden to come to the talk and present the simulation of. So what I'm trying to do here is just demonstrate some effect within a galaxy. The content of this is not very important, but you can see that they have about 100 stars, so that we're talking before that 3 is already difficult, it's impossible. So here they have 116 points, I think, that represent the stars in the galaxy. And you have a tiny clock at the top showing you how things evolve, and you can see that even in this small simulation, this is forming a spiral galaxy with all of the bars, right? And so they made this simulation, or he made this simulation in time to demonstrate this effect, how you can form a spiral galaxy just by some effect. You can see known as by arm, and all of this effect. And how these things are not like permanent features, that over long periods of time the spiral arms change. Right? So this simulation was done in, I think, 1961. And it took months to calculate it on a computer. And well, now this is something trivial, and simulations that are much bigger than that. Students that go in my class, we can do this on a laptop very, very easily. And so this is about 60 years ago, and this, as I said, had 100 stars. And so if I now move to simulation that we do these days, so this is now a simulation of hopefully nothing too dark. should work, maybe. We'll see. Maybe not. Yeah. So now we are flying through a bit of universe. So each of these very white blobs, these are where galaxies are. And then we can see how different bits of matter and all these stars. Now in this entire simulation, there are more than 100 billion stars that are being simulated. So that's 1,000 times 1,000 times 1,000 times more than the previous one. So in 60 years, we have multiplied sort of the capability of what we can do by 1,000 times 1,000 by 1,004, right? This is also because of the evolution of computers and so on. And so now we can do this simulation and test how, this is a prediction of what we think our universe looks like on very, very large scales, much beyond one single galaxy. So, just one quick slide to explain a bit of things that I do on a daily basis. My interest is how does our universe work. I'm not interested in just galaxies or stars, I'm interested in looking at the whole picture. And so we know sort of from measurements how the universe looked like very, very early on. We can do these measurements of the cosmic microwave background. We can measure how the universe looks like now just by looking outside, right, on a not too rainy day. And then, we have all of these questions. How do we go from the start to the end? And we have all of this possibility. What is the nature of dark matter, which you may have heard of is something we don't know. There may be dark energy. Maybe we don't have to change the laws of gravity. Maybe the speed of light changes over time. Maybe there are extra particles that we don't know about. And so all of this, well, we have to teach, we have to go back to our computer scientist here and tell her, okay, put all of this theory in your computer and then tell us what the universe looks like. Then hopefully in a few years we'll have a satellite like the Euclid mission here, or the satellite that Anna will be talking about in the next talk, that can observe this, and then from all of these theory, right, we can then test and say, okay, which one of these makes images that correspond to what we see in the sky, and then we can cross them out. Hopefully you can cross out as many as possible. And maybe there's one left at the end, maybe not, and we have to go back to the drawing board. So for instance, here's an example of this where you have 3 different versions of what dark matter would be like, and then you can see you can make universes that look a lot clumpy, or something that has like long-ish filaments, or some sort of different intermediate step. And so all of these things at the simulation we can run, make predictions, and then say, okay, now I've done my theory calculation, I've done my computing calculation, that's enough for me. Now I have to trust other people to go make observations and tell me whether I'm wrong or not. And I'm probably going to be wrong. Now, you may realize I've shown a computer like this. So this is my Lego model, and which is not the usual thing. You're probably used to more like a laptop or a desktop computer. So maybe one legitimate question is, what does this computer look like? So this is a computer in Munich, in Germany, I visited a couple of years ago. And so the reason that I had this sort of Lego thing is because these are like, you can think of one of these here, one of these racks, that's about the size of a big fridge. Right, pretty tall fridge actually. And then in there you have all the sort of, every 10 centimeters you have like a motherboard with all of the CPUs. So in this computer here, you have about 150,000 regular home computer all bundled together. Right? And then you have the cables on top, and it's a horrible mess. And it's so loud in there, you actually have to wear, what do you call these things? Like not the earplugs, but even the things that go on top of the ears, because it's so loud because of all of the fans trying to cool down. So these are really, really powerful computers. The Netherlands also has one, so this is the one in Amsterdam. It's called Snellius. It opened in October last year, so the Dutch national supercomputer. These are all kinds of images that come from all the simulation that it provides. So there's like some people biking, which I guess is a very Dutch thing. And there's some astronomy and a bit of everything. And then one of the things that people like to quote is the number of calculations the computer can do. Now it goes into really, really big numbers. And so the units people like is to say this computer is 14 petaflops, which is something that probably means nothing to most people. But what it means is that it can do 14,000 operations per second. So that's a number of calculations this computer can do. Every second it can do that many multiplications or that many additions. Right? A home computer is about 20,000 times less powerful than that. And so these are the kind of computers we can use to make the simulations we have. And so this is sort of Pretty big machine for, if you look at what is available, it's one of the biggest machines in Europe. Today, the largest computer in the world was announced, and it's 80 times larger than this. So that's the largest machine that is available today. Since today, I don't have an account, so I can't tell you whether it works, but this one is pretty fun to use. And just to finish, I don't have much more to say, just another movie from a completely different scale from the simulation we did. Now this is sort of a moon forming scenario, so you had a, if I go back, what you have here is there's an early Earth and an early moon, and then you don't want to be on the Earth on that very day, but this is sort of an explanation of how you can form the moon in some of these simulations. So we can have fun crashing things. Again, you can't go in the lab and build a fake, like an early moon and an early Earth and make them bang each other and get the moon out. But we can do this in a computer, and we can do is we can try different angles, we can try different sizes, try different heats, and then see which one gives us a moon that may end up in an Earth that looks like the thing. And so that's the kind of things we do. We run simulation to try to make predictions from theory that other people can go and test in their observations. Thank you very much.
Great, thank you, Matthieu. I'll let you take questions because we only have one mic. So if anybody has any questions, now's your chance to ask.
Thank you for your talk, very interesting. Question, when do you think you will get an answer for a lot of these things that you're looking for?
Right, so, well, it depends on the questions you're asking, but for instance, I mentioned, so this is the Euclid satellite, which is a big European consortium with about, I don't know, like 2,000 people working on the project. And this is going to launch, in principle, next summer. And then it's going to take 8 years of data and produce a map of the sky which is so precise that we should be able to know which one of these, well, at least we don't know which one of these, but we'll know many of these will have to be wrong because they are so different, right? There are really big differences between these, at least to a trained eye, at least there are really big differences in these, and we should be able to tell really well what the difference between these. So I expect in the next 5 years, we can rule out a lot of these models, and then we'll see what survives, and then probably we'll have new questions, and we'll need a new satellite. There was another question at the back somewhere? I'll try to run.
Yes, when do you think that quantum computers will be usable, and will they actually make a big difference to your work?
Right. Yeah, so quantum computers, I think everybody else in the corridor where I work, they work on quantum computer, at least on theory. They work on building, thinking about how they're going to work and so on. So, not quite today. I don't think it's going to make, as far as I know, none of the big calculations type we do, or that are done, for instance, in engineering, or like in coastal defense or weather forecast, many of things won't necessarily be changed much by quantum computing as we understand it now. But at the same time, since we don't, I don't have a computer I can go and play with, I can't tell you whether I could make things go better because I can't just try it out. So it's a bit of an open question, but it's unclear whether it will be a big change for this. The thing that will change a lot is a lot of cryptography, security. A lot of things will be completely revolutionized by quantum computing. Whether it will help that kind of science, I honestly don't know, but I don't think so.
Sorry, another question. It's always nice to know that what you do actually makes sense. So, if you start looking back, where in the history do you think computer simulations would have helped a lot in astronomy?
Well, I think a lot of them, for the reason I gave, right, a lot of the things we know today are all being backed up by simulations, because we can't make experiments. So a lot of the theory developments come, and I showed this like very early movies of this galaxy forming a spiral arm. So this is something that was used already 60 years ago to make predictions. Whether earlier than that could have helped, I don't know. I think one of the calculations that people maybe 150 years ago people were doing were calculating orbits of planets to see whether there were exoplanets, for instance. Probably having more precise calculation and ability to perform this more precisely and more quickly might have helped, but at the same time they found all of the planets, so maybe they were much cleverer than me and they don't need a computer.